Now, these two lectures are helping the transition towards more quantitative and more technical work, so to speak. And so I have this honor to start making things more mathematical, more quantitative. And I think that's very interesting because that's where the rubber hits the road in terms of fairness and what does it mean for an algorithm to be fair. At the same time, it's a big responsibility. I'll try not to kill you with formulas, but I think it's inescapable that I'll have to show you some formulas here and there. So I'll do my best to give you a taste of the quantitative aspects without making it excessive. And here is our agenda for the next 2 hours. I'll describe information access, building on what Carlos told us earlier. And then I'll start describing fairness and information access with a few examples, and then describing sources of bias and axes of fairness. We'll see mathematical formalizations, and then just a little taste of fairness enhancing interventions, or what have people been proposing in terms of solution to improve the fairness of an algorithm. And if at any point you want to jump in with questions, either in the chat or if you're feeling brave, opening your microphone, that's great. And I'm super in favor of interruptions. All right, so let's define information access. Let me hide this ugly thing. Okay, so information access, now I want to try to convince you that it's a useful paradigm. It's an abstraction, but it encompasses a lot of different applications like search engines, media streaming platforms, marketplaces, job platforms, which is why we're here, and social media. So everywhere where you have a ranking component, essentially. So to get us started, if you'd kindly go to WooClap and now change the code, FINDHR TS06, and you can select multiple options for this. Which of the following services are strongly based on information access systems? So we have LinkedIn, Telegram, Spotify, Amazon. Oh, how do I hide? Oh, like this. Nice. Okay, I see 26 answers so far. I'll wait a little bit longer.
Yeah, we have 60 people.
Sorry, say again?
60.
60
people, yeah.
Okay, good.
61.
Okay, then maybe, yeah, let's keep the 40 mark for moving ahead with the answers.
Yeah, the first access is the longest.
Yeah, that is true. Okay, and yeah, it's time to get going. All right, so the correct answers are 1, 3, and 4. Yes, and Telegram. Well, the main component there is a messaging app. It certainly has some ranking features, but I wouldn't say that it's strongly based on information access. Okay, and to keep us going, we'll have a couple running examples throughout this lecture. One is going to be a job portal, because again, that's why we're here, and a second one on a music streaming platform. Okay, so information access is an abstraction, and it encompasses these systems with these characteristics. They provide ranked outputs, so they take items of uniform nature and they put them in an order for us, according to ideally an idea of relevance, and that's more often than not, maybe always, personalized. So it's not like it's subjective relevance. It's not like it's objective. There's always a subjective component to it. And then there's repeated decision making. So, for example, YouTube's algorithm, it keeps making decisions over and over again. Every time we hit refresh, that's a new decision about what are we going to show to this user. And there's a multi-stakeholder structure. So there's the producers of content, there's the consumers of content, and there's the people who are featured in the content. And these are all different stakeholders, and ideally, these platforms should work well for each of these stakeholders. All right, information access fundamentals, or the, let's start with basic terminology. So items are the things we're ranking, CVs or songs. Item producers are the ones who create the CVs. So these are the job candidates or the songs. So these would be the artists. And then the consumers are the recruiters in the case of the online platform, and users in case of the music streaming platform. So producers of items, consumers of items. I'll use this terminology throughout the lecture. I hope it's clear. Next, there's an information need, or what type of items consumers need. For example, this can be a job description that's in the recruiter's mind. This is their information need. And the query is the expression of their information need. So maybe they'll issue a few keywords. And in response to these keywords, they'll get a ranking, so an ordered list of items that's presented to them. Presentations are normally a list. Sometimes it's a list of verticals, so it's like more like a grid, but typically it's like a linear ordering of results. And then we'll talk about user satisfaction. So these are the signals that it's a signal that consumer found something relevant, something like skipping a song or liking a song, or in the case of online job portals, it could be a recruiter sending a message to a candidate. That's good. Even better if the candidate somehow accepts the message, so maybe responds with a positive acknowledgement. So how are these developed? Here is the anatomy of an information access system. Quite complex, I know. We'll unpack it slowly but surely. We'll start from users and items. So information access systems maintain a representation of users and items. So users rely on the information access system to get their items. The IAS processes their queries. And the system holds these representations of items. So it leverages the neural networks that Carlos told us about earlier. Typically, nowadays, a lot of this is done through neural networks, which sort of condense our profile as job seekers. And they also condense the job description into a numerical form. And then they do this matching, for example, through the two-tower system. So the final or the intermediate representation of mathematical representation of recruiters, job descriptions, and candidates, these are maintained by the system. And for example, here they're exemplified as these green squares. Okay, and given the definition of query we had earlier, a query can be either a thought in the user's head, a user's listening history, or a sequence of keywords. Now also here you can select multiple of these. Okay, let's see the right ones. Yes, very good. So sequence of keywords, definitely. Users listening history also can be an implicit query in the case of recommender systems, but this was a very tricky one. I only put it here. These questions can be tricky, but I put them here to keep you thinking about this. And I thought in the user's head, no, that's an information need, but maybe one day, or we're already getting there, and we'll have human-computer interfaces that are like brain-computer interfaces. But until then, no. All right. And then we do retrieval and rendering. And this is the core business of an IAS. So in response to certain user actions, IAS retrieve a list of items that should be relevant for our users. And then they rank them according to different criteria, platform utility for sure, and user satisfaction. And these two sometimes are well aligned, sometimes not as much. And the top items are rendered to the user, so they're shown in a list or a grid. And so we're here now. The retrieval took place, the items have been ranked, they have been rendered for the user, and the user now sees the items. And they behave in one way or another. And at this point, it's important to try and understand the users. So users are going to interact with the item presentations with providing implicit satisfaction signals. And again, these have to be interpreted as satisfaction, but it's difficult because interactions are mediated by retrieval and rendering. So I'll be way more likely to click on the topmost item, for example, in a search engine, because I sort of trust that the search engine is doing a good job for me. And so if I click the first item but not the second, does it mean that I prefer the first item over the second in general, or that I prefer it just because it's being shown to me by the information access system? Now, that's a tough question. So behavior understanding is complex. And this is done by storing some information about the user and then analyzing that information to understand the user better. And then there's evaluating and updating the information access system. So at an individual level, if we consider individual users, we want to understand them. Say we are developers of an IAS. We want to understand our users to improve the experience for them. Of course, not too much. We don't want to be creepy, as Carlos was saying. But it's important to maintain a acceptable level of performance. We want to then aggregate at an aggregate level. We can understand if more users like a certain ranking strategy more than another, if they like the results provided by a ranking strategy more than another, then that ranking strategy is better. So we can update our ranking strategy and use this new one because users like it better. And we have to figure out all of this. These like item relevance, the relevance of items for users is unknown. It's a super central concept to information access, but this is not known. So it to operate based on estimates. Okay, give me your opinion on this. Which one of the following are plausible signals of interest for a user item pair? So for example, for a recruiter and a CV, is it a click? Is click a possibility? Reporting this content as inappropriate? Interacting for 15 minutes or interacting for 10 seconds? And again, you can select many of these. I think you should. Okay. Yes, super. Reporting content was interesting. Yeah, maybe it's like the reverse of a signal of interest. It's a signal of like that it's triggering in us something negative. So in this sense, yes, that's a good guess. And everything else, yeah, of course, 15 minutes looks more interesting than 10 seconds, but also 10 seconds can be a weak signal of interest. It's stronger than neglecting the item altogether and just scrolling through. Right, so we're here. We're doing behavior understanding, which allows us to improve retrieval for the next round. So the next time the user logs in, maybe we'll be able to show them more relevant content, and we can do evaluation to improve our system in general. Now, evaluation. So when I say simulated evaluation, this matches what Carlos was calling offline evaluation. So it can be a good replacement, at least to eyeball performance of a system, replacing the risks of doing online evaluation. Because if you're doing online evaluation, you're essentially, it's showtime for your new algorithm. You're using it to into the product, into the system that's being used in that moment by real users. So there are risks. So to do a first check, you want to do offline evaluation. And you need this idea of a ground truth knowledge of relevance. Like maybe you need somebody to annotate for you whether a given document in a search engine setting, whether a given document is relevant for a given query. And this is going to be based on user behavior, the whole evaluation, and their so-called item consumption. So how do we think that users are going to traverse the ranking of items that we show them? And we have a top-heavy assumption here, but we'll see more about this in a minute. And we'll see more about this right now. All right, so here we have a ranking. These are items that are being ranked by an information access system. I'll call rank 0 the topmost item. So this is the item that the system thinks it is best. And then in rank 5 is the bottom item. And I think I can hear someone. I'm not sure.
Yeah, I'm muting everyone. I also muted you. So you have to unmute.
Okay,
Yeah,
am I back?
okay.
Good. That was a very strong censorship, very efficient. All right, so these are items that are being ranked, and we're color coding relevance. So we'll say that Y is the relevance of an item, and dark green corresponds to high relevance. Let's say that the maximum relevance is 1, and light green corresponds to low relevance. And let's say that the minimum relevance is 0. This is just a mathematical convention. So this is a perfect information access system in the sense that it's done a great job. It's ranked items very precisely according to their relevance. There is no item that I would now move above or below. I wouldn't do any swaps because this is perfectly color-coded according to relevance. Good. Now comes a second information access system. So this is like a second algorithm. And the second algorithm is giving us this ranking here. And I think it goes without a doubt that in terms of ranking utility or like the average relevance for users, it goes without saying that the first information access system is doing a better job than the second one. So we're very pleased with that. We don't need any strange things here. But now comes a third information access system, and all right, it's definitely worse than the first one. But what about if we want to compare the second one and the third one? Which one is better? Because now, I mean, if we look at it, the second one recognizes the most relevant item and places it at the top. But then for every other item, the ordering is reversed. So that's far from ideal. And the third information access system has sort of done the reverse. So the most important item is at the bottom, which is terrible. But then everything else is ranked well. So the relative positions of items are correct. So which one is better? And we cannot tell unless we have a model of ranking importance, the importance of different ranks. And that's what we'll do here. So this is what we call normally a browsing model. And it's essentially the idea of attaching an attention weight to each ranking. And attention weights typically go like this. So we have a big weight in the top position, and then the weight starts decaying very quickly. And then we have our ranking. Let's use this fancy letter tau to indicate a ranking. And again, here we're color coding the relevance of items. So the top item is super relevant, the bottom item super irrelevant. And what we can do is do a weighted average of their relevances. So we take the weight according to the attention that we think each item is going to get, and we multiply it by the relevance of that item. And then we sum everything and we divide by the total, which here is 6. And we get this number, which is essentially, as I was saying, the weighted average of relevance of items weighted according to a browsing model. Now, we're not saying that this is how ranking works normally. And that's not how we as users derive our utility from a system. But this is just a model, and it's been found time and time again that this model is quite useful to eyeball the performance of ranking systems. So that's why we use it. Okay, question. This is more of an attention check. The best rankings, let me remove this. The best rankings present relevant items toward the middle. Okay, let's see. False, yes. The most important items, most relevant items should be at the top. And well, if there are more relevant items, then yes, also toward the middle. But what is very important is that the top rankings are filled with relevant items. The top ranks, sorry. Okay, so time to start discussing algorithmic fairness in this context. And let me start with something I deeply care about. So, well, if I have to give a quick definition of algorithmic fairness, it's probably going to be this one. It's the idea that algorithms should work well for everyone and avoid harmful discrimination. Now, this comes from normative ideas of what it means to have equitable treatment. So, for example, this can come from an exogenous right, like contracts, which say everyone should have their lawful amount, and what counts as lawful, well, it's going to be written in the contract somehow. Or compensation, we should give more to those who bear higher costs and should therefore be compensated. That's the idea supporting affirmative action. It can be based on reward and merit. So we want to give more to those who contribute the most. it can be based on fitness and relevance. And this is central to information access system, but sometimes it can be nebulous. So I just want to say that fairness measures should always be well justified and beware of weak normative reasoning. So every time somebody comes up with a measure, shows you a measure, or tells you my algorithm is fair because we are equalizing this, question them on why they think that that is important and that that should be equalized, and what is their normative reasoning. This is fundamental. Okay, now a spoiler question. So spoiler in that I don't think we've seen this already, but we're about to. So algorithmic fairness in hiring only applies to job seekers. Do you think it only applies to job seekers, or it could apply to other stakeholders? Okay, see some quick answers coming in. Good. All right, let's see. Yes, I very much agree. I think fairness is about all different types of stakeholders. So fairness in job search. Fairness in job search means answering these types of questions. Do candidates receive a fair set of job opportunities, for example, in the recommendations or ads that they get in their feed? And do they have a fair opportunity to appear in search results? For example, when recruiters issue some queries. And for employers, let us not forget about employers. For instance, minority-owned businesses, do they have their jobs fairly promoted to qualified candidates? Or maybe some employers are being hidden and their job offers are not appearing to candidates. And for our music streaming and discovery service, relevant questions include whether artists have a fair chance to be discovered, whether users receive a good service, and if not, maybe there are some user groups that are systematically being underserved. And these are all relevant questions for the different stakeholders, and ultimately fairness and quantitative notions of fairness try to give an answer to this question, or to more precisely to highlight situations that are critical for these questions. Where does unfairness come from? So this is the picture. Again, a fairly complicated one, but let's unpack it. So data powers everything today, as we commonly hear. It's certainly at the base of data-driven models. And data-driven models are trained, and they then give some results, for example, rankings of job seekers. And these are evaluated, as we saw earlier, also through data. And then once we're satisfied with the system, that system goes into production. And then it's going to be used by recruiters. So ranking results are shown to recruiters, and recruiters have their own individual biases. And then these individual biases, if we zoom out at a collective level, they are societal biases, which are then fed back into the data, because the data is, well, the mirror of society. And so this is a big cycle. Now let's start with data biases. And I want to tell you a little bit about a couple types of data bias that are quite common, and it's easy enough to reason about them. So sampling bias comes from the fact it happens when the data is not representative of a target population. Now, this is a very popular example of an algorithmic fairness evaluation that was done on face analysis software released on the market by Microsoft, IBM, Face++. And the researchers who did this analysis found that the algorithm was performing poorly for women with darker skin. And the most likely reason for this is that the training data on which these algorithms were trained was not, it didn't have many women with dark skin, and therefore this sampling bias led to an unfair algorithm in the sense that this algorithm wouldn't work well for women with dark skin. Then there's measurement bias. Now this one is a bit of a tricky one, but essentially this means that a variable's name, or what we think that we're measuring, is very often just a crude approximation for what we actually care about. So we can distinguish conceptually between a construct space, that's like an ideal world where our ideas live, and then an observed space where that's actually what we get. So in the construct space, we have things like work experience, learned skills, and song appreciation. And these are all impossible to measure, like to even define precisely. What we do have is like how many years somebody spent in a job, what was their GPA, what's the number of likes for a song, this sort of thing. And thing is that the measurement error may be uneven across individuals or groups, and that's especially tricky. So here is an example. Yeah, I have to take a detour here into Compass, but I think it's super valuable because Compass is a textbook example of a controversial system, and which is also unfair. So Compass is deployed in the US to help judges take decisions about pretrial detention. Sometimes a defendant is sent to prison preventively because there is a risk that they will recidivate while being trialed. And so there's an algorithm helping judges take this very decision. And so this is an algorithm that essentially is trying to predict crime, future crime. So this is already controversial, I know, but let's take it at face value. From past crime, ideally, but no, because we don't really know past crime. We know past arrest data. And this is crucial. So here there's a strong measurement bias. And we can see this in these results of the algorithm. So the algorithm can do two types of mistakes. It can label someone as high risk, but in the end, they don't reoffend. And we can find that this is especially common for African-American defendants. And the second type of mistake is labeling someone as lower risk, but then they do reoffend. And this is more common for white defendants. And the reason why this happens is that the data on which these models are trained is such that they end up overestimating the scores for over-policed groups, because African-American people tend to, there's a correlation between ethnicity and socioeconomic status in the US, and poorer neighborhoods tend to be policed more. So it's those neighborhoods where arrest data tends to be higher, also because of these policing patterns. So measurement bias. Alignment. This is something I saw a few weeks ago. So this was on a video recommender system. And now let me tell you that for video recommender systems, I think the objective function, which is like what engineers are optimizing their system for, is invariably a variant of this idea, maximizing the probability that a user is going to watch the recommended video. But in stakeholder communication, this is what they say, that they help users discover videos they love. Now, I'd like you to think about and tell me, if you want to, whether you see an alignment between these two or a potential disconnect.
There is a question, Alessandro.
Yes, please.
I suppose it was related to something before, but I didn't see it before. So based on your ranking evaluation framework, what recommendation would you give for legal in case business want to build an internal framework, compliance and HR? to set the basic principles and steps to understand if your ranking system is giving relevant items on the top ones.
Okay, so is this question about which browsing models and which ranking systems to use?
I don't know, Marco, could you please explain? Yes, yes, the answer is yes.
Okay, so that's going to depend on the situation. So you want to understand your users. Okay, so a very broadly applicable ranking scheme and browsing model is called NDCG, and so that's going to be my first answer. That's a good starting point. But then you may have to refine it because, for example, NDCG has got attention weights that don't decay super quickly. So it kind of models users as quite patient. Whereas in some settings, maybe users are going to have a look at, I don't know, 3, 4 CVs, and as soon as they find enough CVs that are relevant, then they'll stop browsing. So this is going to be very much dependent on the context, and in the context of hiring, it's going to be dependent on which stage of the hiring pipeline we're at. If it's the beginning, maybe users are going to be more patient, and let's say that the recruiters are happy to cast a wider net. Towards the end, they're going to be less patient, and so a quick decay is going to be better. Okay, let's move on. And then there's societal bias. So we're talking about the biases in the data. Now, societal bias is sort of the difference between the world as it is versus what it should or could be. So for instance, these are a couple facts. Students from families of high socioeconomic status attend prestigious schools, and then students of prestigious schools perform better in standardized tests. Now in 2020, and given these two very basic facts, now in 2020, COVID came and UK students couldn't take their A levels. So a UK office decided that they would give grades in terms of A levels by taking into account past school performance. And this, of course, ended up penalizing students from certain schools. Now, there isn't any bias in the data in terms of either measurement bias or sampling bias if we take the data at face value. But there is an inherent problem here. There is a societal bias, and do we want a model to pick on this societal bias? Because ultimately, a model trained on this data will reinforce existing inequality. And so again, this is a normative question that's connected to this type of bias. Okay, other sources of bias. Short-sighted training. So the way training and evaluation works is essentially they do an average across all users, which in a way is sensible, but this means that in this way they will end up focusing on majority groups. Minority groups are unlikely to shift this average by that much. They cannot move the needle a lot, and that's a fact. So unless we take them deliberately into account, a model trained and evaluated without attention to fairness is going to underperform, most likely for minority groups. Then we have individual biases that we saw earlier. So can have their own biases, even if an algorithm is showing a ranking that's very gender fair. Recruiters may choose or a ranking that is very fair according to ethnicity. Recruiters may think, no, this customer, they really care about cultural fit, so I will call candidates who are locals, and candidates who have a migration background, I will call them only if I cannot find someone else from this very country. And this is something that just happens, right? So it's important, of course, that the recruiters remain in control, that we retain human agency, and at the same time that we have equitable decisions. So these systems should be developed with human-machine interaction in mind. Okay, quick question to summarize this. Which of the following biases do you think can be best addressed with technical fixes? Societal biases, data biases, training and evaluation biases, or individual biases? Let's see. Yes, super. Data biases and training and evaluation, most likely. I mean, they're not solvable, but they're more easily addressed with technical fixes. Thank you. I see a question by Elizabeth. Can societal biases be fixed with the kind of technical affirmative action? E.g., if it is known that a system is based on data where a certain group is disadvantaged by factor X, can the system be built in a way that advantages this group by factor X? Okay, it's it's a great question, and I think it's one that could spark a very long debate. My short answer to this is, in principle, yes. I mean, it's technically feasible. Whether it's desirable, I mean, it is a fix, but it is a little bit of a cheap fix. It's not really acting on the structural causes. It's sort of injecting equality into the system at the end of it. So it does come with its problems, like maybe people from the other groups feel like this is unfair. But it can help improve the situation. For example, with aspirational models. So say there's the so-called Scully effect, for instance. There's this theory that a lot of women in STEM today have been inspired by seeing Scully in X-Files. So having these positive role models, and it's easier to see them with affirmative action, right? So this may be an argument in favor of affirmative action and even algorithmic affirmative action. Now, whether this is legal, my understanding is that it's debatable, and it's probably not. It's more on the risky side of legal risk, especially because affirmative action needs to take into account different factors holistically, at least according to European law. And algorithms are not very good at doing that. Algorithms tend to be quite brittle about how they use data. Great question. Thank you. Sorry, let me just check that I can still hear. Yes, nice. Okay. So axis of fairness. Fairness is complex, it's nuanced, it's context dependent. So whenever we talk about fairness, we should be clear about what harms are we trying to prevent, who is being protected, over which time horizon are we considering, and which measure are we adopting. For types of harm, there can be distributional harms. These are probably the most visible or the ones that come to mind first. So it's whenever we're distributing a given resource that is limited. And when we do this unfairly, we're denying equitable access to loans, to healthcare, education, welfare. By the way, I'm not making any of these up. These are not like guesses. These are settings where algorithms are being used today. And also attention, of course. So user attention with streaming platforms, but also recruiter attention, buyer attention on marketplaces. And so this is what information access systems, what is most relevant for them. They distribute attention, and if they do this unfairly, then this is a distributional harm. Now, they're also called allocative harms, and an example for us is when maybe in a example that is related to online hiring, this could be the case when female candidates are systematically ranked below male candidates with the same preparation. If they have the same preparation, then we would expect that sometimes male candidates come before, sometimes female candidates come before. There shouldn't be any systematic preference. Okay, so question, true or false? Distributional harms include discriminatory procedures through which decisions are taken. I see it true, but now I'm going to hide this. All right, let's see. Most people said true, and I can see why. But distributional harms are, they essentially take a consequentialist approach. I think you heard about consequentialism in previous sessions. So it's this idea that we only care about the outcome and will just judge fairness based on the outcome, but not based on the procedure. So it's just the outcome of the distribution, but not the way that the distribution took place. And we'll see about this in a moment. But first, representational harms. So these are inaccurate representations, often stereotypical. Here we have search results for images. The query at the top, so this is a result page. Here the query is compassionate person, and below, different query, competent person. Now there's clearly an imbalance in these search results. There are more women at the top and more men at the bottom. And this is in accordance to one of the most well-studied gender stereotypes in psychology, which tie communion and warmth to women. So these are traits that are perceived as stereotypically female, and agency and competence as stereotypically male. And these search engines may end up reinforcing these ideas in users with these results. Same as could happen with an algorithmic hiring system. So if a recruiter issues a query for a Java programmer and the results only contain male candidates, now of course this can be damaging for female candidates who are not being shown. And this may also reinforce gender stereotypes in recruiters who get this confirmation of, yes, indeed, this job will only find results for male candidates. So this is a job that is for men in a way. And then we have procedural harms, which is what the question was about. So procedural harms are only focused on the decision-making process rather than the outcome. So maybe an example of process and how it can be fair or unfair would be the way rejected candidates are treated, whether they get a notice or an explanation. Now the outcome is decided. It's not a matter of outcome. It's a matter of how the outcome is communicated and how the whole procedure is taking place. Okay, protected groups, which identities should we consider when we measure fairness? So we'll start from individual fairness. So individual fairness requires that similar people be treated similarly. And so slight changes in the features, so slightly changes in their profiles should not cause major changes in outcomes. If I have one less month of experience than someone else whose profile is otherwise identical to mine, then our position in a ranking should be very, very close. It shouldn't be the case that I'm placed at the bottom and the other person is placed at the top, unless everybody looks like us. And group fairness is a different idea. It seeks to avoid systematic discrimination and unjust disadvantage against socially salient groups. And now that we're talking about groups, intersectionality is an important concept. So it's, broadly speaking, studying systems across multiple sensitive attributes, so at their intersection, like this study we saw before. And sensitive attributes are of two types. The first one is socially salient attributes. What does this mean? These are attributes that have been recognized as being drivers of discrimination in the past. And places where this recognition happens is, for example, the law. Anti-discrimination law is one such place. Here, for example, we can have a look at the Universal Declaration of Human Rights, which says that all the rights and freedoms should hold without distinction across race, color, sex, language, religion, political or other opinion, national or social origin, property, birth status, or other status. So this is a good place to start from, and these are some of the traits that we may want to think about for fairness, and that we should think about. Or they can be context specific. So automated speech recognition, for instance, we know that it's likely to have disparate performance across different English dialects and speech impairment because, well, it's harder to recognize speech from speakers with speech impairment. Also, they are less common in training sets. So again, it's more likely there is this, this sampling bias, if you will, that we saw earlier. And so this is something that we know that is specific to this context and that we should take into account where we're measuring fairness in automated speech recognition. Question: pregnancy status is a sensitive attribute. Is this true or is this false? Let's see. Yes, most people said true, and I think it's so closely related to sex, which is recognized as a protected attribute, that in itself pregnancy status is protected. So sometimes we should have a broad interpretation of these attributes. Okay, and now we're ready to start going into fairness measures, the dreaded mathematical part. But we'll be kind, I promise. So let's start talking about, I'll give you the two simplest fairness measures that have been proposed. The first one thinks about acceptance rate and tries to equalize it. So the idea here, because again, it's very important that we try to clarify our normative reasoning, otherwise we're going nowhere. So here the idea is we should hire, I'm not saying that this is correct, I'm saying this is a potential point of view. So we should hire a similar proportion of men and women. So the worldview here is that we are all equal, that there are no innate differences between groups, and that any differences derive from structural bias, which should be compensated. This is the normative reasoning underpinning this. This is also called independence, demographic parity. It has various names, this criterion, and this is what it looks like mathematically. So it's asking us that the probability of hiring, given that we are that the candidates are men, is the same as the probability of being hired, given that the candidates are women. This is especially important in job search in the US because it's connected to the 80% rule and disparate impact, if this rings a bell. This is essentially a rule of thumb that can sometimes count as first evidence that a hiring algorithm or procedure is being discriminatory and is having a disparate impact on different groups. Okay, and then true positive rate equality. Now here the idea is that we should hire a similar proportion of qualified men and qualified women. And the worldview here is what you see is what you get. So what we see in the data is correct. So measurement error is negligible and societal bias should be accepted. This is sometimes called also separation, equalized odds, equal opportunity, and it looks like this. So the probability of hiring, given that candidates are men and appear to be qualified, should be the same as the probability of hiring, given that candidates are women and they appear to be qualified. Now, appear, I want to stress it because, again, being qualified, we saw earlier measurement error. Being qualified is something that exists in the construct space, but we'll never be able to measure that appropriately. We can only have some crude approximations for that, so it's going to be an appearance of qualification. Okay, so that's algorithmic fairness in general. Now let's take this into the information access domain. So, well, what are the peculiarities here? Multiple stakeholders. We talked about this enough, I feel. There are many stakeholders in information access systems, and we want to be fair for each of them. Yeah, let's also skip this one. Okay, and we care about joint fairness. So we want to be fair across different groups of candidates and employers, or for music streaming, creators and users. And there can be cross-group harms. So underexposed groups of candidates, they can be harmed twice, both as item producers and as data subjects. And at the same time, so say a platform works poorly for a group of users. Maybe think about music streaming, and now that platform doesn't work super well in a given country for users that are in a country outside of the typical user base. And this is something that happens fairly often. Now, this may discourage the primary audience of producers in the same group. And so it may also cause something like a disenfranchising circle or a vicious circle. And so different types of fairness can also be connected to each other. Okay, another super important property of the decisions taken by information access systems is that they are not independent. So let's take a query for a controller. We're searching Amazon for a controller. These are the results we get. And so say we want to match the relevance of these items with the attention they get, because we subscribe to this idea that we should reward relevance. And so fairness in this case could mean let's give items attention proportionally to their relevance. And here relevance, for example, could be the stars, and it kind of looks like this. Now, can we match relevance with attention? Attention looks like this if we have a very steep decay. So, okay, item 0 gets this much attention. Item 1 has a similar relevance. Can we give it similar attention? Well, maybe we can push it up, and then it's going to get the same, this much attention. But if we push it up, then we're pushing down someone else, and that's the key thing. We cannot rearrange these to match attention and relevance. And so we cannot allocate the same exposure to two items. And that's why decisions are not independent. But decisions are repeated. So maybe the next time we issue this query, these are going to be the results. And are the reverse of the previous ones, then attention profiles look like. So item 0 in sum would get, if you sum these bars, now all of a sudden you get something that starts to look like the bars of relevance. So we can do this over multiple impressions or multiple queries. We can match relevance and attention and leverage the fact that decisions are repeated. And then outcomes are subjective. So these are very much user dependent. And item producers, say I sell bicycles, then I of course care about exposure of my bicycles, but I care about exposure to items who will find them relevant, not to items who are looking, to users who are looking for cars. That's going to be completely useless for me. However, it's also true that IAS can influence long-term user preferences. So think about when you discover a new genre on a music platform, or also polarization, for example, when we think about news consumption. All right, and now we're well equipped to start to look at the mathematics of this. So we'll need a little bit of notation. I'll try to keep it as light as possible and introduce it only when we need it. So we'll use I for items. We have item number 0, number 1, all the way to number n. And we have tau for a ranking. We use tau of 0 to indicate the item in position 0 in tau. We've seen attention weights already. We use k for ranks. And for example, when we say that tau of k is equal to I, we're saying, for example, here tau of 0 is equal to I. We're saying that the item in position 0 in ranking k is item I. And this is just a way to say the reverse, so that item I in ranking tau occupies position k. And we use this notation with the belongs to symbol to say that an item belongs to a sensitive group. For example, this job seeker is a woman. And then we'll have a target or ideal distribution for, typically for recruiter attention, which helps us ground our normative reasoning for how much exposure should we grant to men, to women, and non-binary candidates if we're considering non-binary gender as our sensitive attribute. And this is just an example. It can be any other sensitive attribute. Maybe we'll consider, I don't know, ethnicity or disability status. It is useful if we can define a target, and every fairness measure you'll find defines a target either implicitly or explicitly. So I think it's best to try to be explicit about it. And yeah, it's typically defined as a distance from a target. Okay, producer fairness. So in our case, producers are, for example, job seekers, people who produce the CVs or the profiles that are being ranked. So let's say we have our target representation across 3 sensitive groups. Maybe this is going to be 1/3, 1/3, 1/3 for the sake of simplicity. So this is among the top 10 results, how many should belong to a given sensitive group? And the answer here is we want to give everyone the same representation among these 10 items. Well, it's not divisible by 3, but you get the idea. It should be 1/3 for every different group. And then, so this is the target. And then we have the actual representation. So in the actual ranking, how many items are there from group A, from group B, from group C among the top K? We count them and then we divide them by K, and this is the true representation that they're finding in this ranking. And group representation is typically defined like this. So it's let's just look at the brown thing for now. It's a divergence, or essentially a distance between the target and the actual representation. So this is expected. Fairness is always a distance between a target and an actual representation. In mathematical terms, 80% of the time you'll see definitions that are like this. Now, at which rank? At 10, 20, 100? Well, maybe we want all of this. So we'll sum over different rankings, over different ranks, and then we'll do a weighted average. And so essentially we're measuring a distance between a target and a true representation. And this is the gist of group representation. So if this is clear, I'm super happy, because it's like a very useful first achievement for this mathematical part. It's a very common paradigm to define it like this. Okay, now let's start talking about exposure. I have to introduce a new symbol, which is relevance. We'll use Y to denote the relevance of an item. So maybe a candidate who is super relevant for a given position. And equity of exposure, the normative reasoning says that items should be allocated exposure proportionally to their relevance. So we can define it like this. Let's call E the actual exposure that they're getting, T the target, and this is going to be essentially the attention weight, the actual exposure that they get. And we're saying that this should be proportional with a constant C to their relevance. And now if this number is very large, it means that this candidate is getting more attention than they deserve. And if it's very small, it means that they're getting less attention than they deserve based on their relevance. And we saw earlier that this is most likely hard to satisfy with a single ranking. However, ranking decisions are repeated over time. So it's difficult to match this and this to make their difference equal to 0. But if we have another chance to take a decision and a different ranking, now it's easier. If we can sum these two, they become closer to this one. So with time, it's more easy to get this match over multiple rankings. And let me ask you a question just to see whether everyone is still alive. Equity of exposure is a measure of producer fairness. It must be obtained with a single ranking can be an individual measure. Which one of these are true? Let's see. Yes. Indeed, it is a measure of producer fairness. It can be an individual measure, and it mustn't be obtained with a single ranking. We can have multiple of those. Now, maybe here the confusion for the third one. It can be an individual measure. It doesn't have to be. So let's see that. Group exposure. So equity of exposure for groups is very similar. This is the normative reasoning. It says that items in groups should be allocated exposure proportionally to their overall relevance. So if the first one here, oh, sorry, I should have, well, it doesn't matter. The first one here is the one we saw earlier for individual fairness. And now for group fairness, we're just going to do a summation over groups. So we're going to say that there is a target for the group, which is equal to the sum of the targets for individuals. Sorry, this one is the target. And there is a true exposure, which is the sum of the true exposures of individuals. And we'll take their difference, and we want this to be close to 0. If it's large, it means that this group, men, are being exposed more than they should be according to their relevance. And if it's negative or very small, it means that they are being exposed less than they deserve. So they are being ranked lower, essentially, than they should be. Okay, then we have pairwise fairness, but I think I want to spare you this one. So pairwise fairness is a fair ranking construct that doesn't have a super clear normative reasoning. So in the interest of time and your mental sanity, we'll skip over this. And we can move to consumer fairness. So far we've been seeing measures of fairness for producers of items, which in online hiring settings typically corresponds to fairness for job seekers. Now we'll see consumer fairness, which would be fairness for recruiters, or in the music streaming example, this would be fairness for users of the platform. All right, and the basic idea is that users should get a similar utility or a similar high quality experience. Do we need a little bit more notation? Yes, we do. We need to introduce queries. We've seen those. So users issue diverse queries, and we're going to use J to denote them. QJ is a given query. So now each item has a different relevance for each query. So if there's the query for software developer, maybe my profile is half relevant. If there's a query for lawyer, my profile is 0 relevant. And this is going to be defined with this Yij. So it's the relevance of item I for query J. And if we take into account the fact that item I is ranked in position K, we can also write this asYkj. This is the relevance of the item ranked in position K for the query J. So user satisfaction, super easy to compute. We can just sum over all the rankings. Remember that K is the rank, so the position where an item is shown. So I'm shown several items of different relevance. we sum all the relevance of these items that are being shown as a recruiter, for example. But again, we'll do this weighted average, where the weight is the attention weight, so the one that decays with rank. And this is how we can model. Again, this is a useful model. It's not, it's wrong. All models are wrong, but this is a useful one. This is how we model user utility and satisfaction for query QJ. Okay, and individual fairness says all users should get a similar utility. So my utility as a user is going to be the average utility or the quality of items that are presented to me across all of the queries. So again, we keep using this idea of summing and then averaging. So we sum over all the queries J that I issue as a user, the utility per query, this mu symbol is utility per query, and we divide by the whole number of queries that I issued as a user. And this is going to be my average utility. It's just one number to summarize my average experience with this platform. Of course, it's a crude approximation. And then we can say that this utility, we want it to be close to a target. Now here, defining a target beforehand is very difficult. Typically, the target is going to be based on other users. We can say that this should be, if this is the average utility across users, and my utility should not be too far from the average. And then, of course, we can define group fairness. So groups of users should get similar quality of rankings and recommendations. Again, we use this very simple idea. We do an average over users. So we've seen utility for a single user. Now, utility for a group is going to be the average across all users in that group. And again, we ask that this utility should be close to a target. And once more, it's difficult to define the target, so it's going to be based on average utility. And this is an example of this type of analysis. Here is the retention rate of a platform across different age brackets and across different genders. Retention rate can be a measure of utility or quality of experience. If I think I'm having a good experience, I'll stay in the platform. If not, I will leave. And this is a profile that you can often get in many platforms. They work better for younger people and for men. Okay, any questions so far? If not, this is the last bit, I promise. And the math is over, so well done, kudos for staying so far. And I just want to give you a little taste of, okay, we've seen fairness and how to...
There is a question.
Yes, please.
Is there any measurement metric that considers consumer and provider fairness together?
That is a good question. So the short answer is no, because ultimately they are different points of view. So if you're looking for like a silver bullet that is going to help you monitor both points of view in an efficient way, I don't think that's going to be possible unless we make like huge approximations. What I recommend is having two separate measures for both, because these are different perspectives in the system and they deserve a different measure in being monitored. And it's actually quite normal that for fairness monitoring, that we're going to need a portfolio of measures, not a huge one, because then it's going to become unmanageable. But if you want to visualize this as a dashboard with some dials, and maybe we're going to need, I don't know, 5 dials to keep monitoring a system. And what can we do once we see that a system is unfair? Well, I mean, one solution is removing it from the market, but that's like a very strong solution, and business is not going to be on board with that. So what has been proposed by a lot of smart people who are working on this are different fairness enhancing interventions. And they belong to 3 different families. We can use this pretty useful categorization. And the families follow the cycle of data-driven decision-making. So we start from data, we develop an algorithm, and then from the algorithm, we get an outcome. This person is going to be hired, this person is going to be rejected. So the first family is called pre-processing, and it looks at data. It looks at data even before we have an algorithm. So for example, here we have the brown population and the pink population, and these are sensitive groups. And we want to learn an algorithm that can distinguish the squares from the triangles. And maybe this algorithm is essentially going to be a line. Yes, this is our group, discriminating squares and triangles, but not discriminating between protected groups. So we don't want to discriminate between brown and pink. And this algorithm, it can be something like a line that says people above the line on this side, they are going to be hired, and the ones on this side, they are going to be rejected. But this line doesn't look super fair. And that's because there's this information on protected groups that is encoded in these 2 features, even if these 2 features are something else. But maybe there's a little bit of information on ethnicity because of languages that are spoken. So if somebody says that they speak a foreign language, then it's quite likely, for example, a language outside of Europe, if the position is in Europe, it's quite likely that this person comes from outside of Europe. It's not the only possibility, but there's some information, some correlation there. So what preprocessing does is it takes this data and projects it in such a way that there is still this distance between squares and triangles. So squares are above triangles. This relationship is maintained. And at the same time, pink and brown points are superimposed to each other. So they cannot be distinguished anymore in the data. And this is one form of preprocessing. It's a very common idea. Okay, this is the last question I have for you. Preprocessing interventions take place after training AI models. Is this true or is this false? This is false. Very good job. Indeed, it's typically an intervention that is done on the raw data before feeding it to an algorithm, which is what in-processing does. So in-processing, this is the second family, it takes into account an algorithm. So algorithms are typically trained, AI algorithms, to optimize accuracy. And accuracy is like the average performance across all items and all users. And now, wait a minute, but if we just decided that accuracy or performance is not all we care about, but we also care about fairness, then how about we make fairness part of the objective of the algorithm? And this can be done. It works in principle. I mean, it gives rise to some algorithms that can behave better sometimes. It doesn't mean that then those algorithms, once they're trained like this, I don't want to give you this impression of techno-solutionism, because that's also very dangerous. Doesn't mean that once we train an algorithm like this, putting a fairness measure into the objective function of the algorithm, it doesn't mean that that algorithm is fair once and for all. We'll have to keep monitoring and evaluating it, but it's an idea for improving from the perspective of fairness. And finally, and this is the last thing for today, post-processing. This is the third family. So post-processing approaches, they explicitly take protected attributes into account to modify the final ranking. So let's start from this initial ranking. We have some pink items, some brown items. Here we have a cutoff threshold for selection. So this means that we'll end up selecting 3 pink and 1 brown. And this is not super fair if we, for example, want to have equal selection rates. So one approach to make this more fair is to split this ranking into group-wise rankings that preserve the relative ordering. So here, every pink item is in the same relative position as they were before. These arrows do not cross. We do the same for the brown group. And then we do a re-ranking where we explicitly do some interleaving, and we say we have 1 brown, 1 pink, 1 brown, 1 pink. This is just one way to obtain equal representation at different positions. And so this is an equal representation ranking that has explicitly taken the protected attribute into account to modify the final outcome. And this was the third family. So now we're ready to summarize. I just want to do some shameless self-promotion, and if you're interested in these topics, chances are that you are. So fairness and bias in algorithmic hiring, we have a multidisciplinary survey on this with several co-authors are teachers in this course, so you may find it interesting. I'll just leave it here for a reference as I go. And the first point from this lecture is that information access systems are pervasive, and they are a useful abstraction, definitely for online recruitment algorithms. Their peculiarities are reflected in measures of fair ranking. So for example, multiple stakeholders means we'll have multiple measures. Decisions are repeated and they are mutually dependent. So, and fairness measures for IAS, they must take this into account, and they do. And finally, fairness is context dependent and requires contextualized normative reasoning. I want to stress this once more. If somebody comes to you and tells you this algorithm is fair, look, I've equalized these 2 numbers, then you really want to ask them, what are those 2 numbers and why should we care about them? Why is that the important fairness measure? Because it can be defined in many different ways and you cannot have it all. So we need to choose, and we need to choose carefully. And with that, thank you. If you have any questions, I'll be very happy to answer.
Can you see the ants on the screen?
Sorry, say again.
Did you see the ants? The ants?
Ah, no, I didn't see the reactions.
On the screen. Excellent lecture, thank you.
Thank you so much.
Thank you. Now you can see the chart.
And I promise, Maria, that there will be no quiz on those formulas.
So happy to hear that. Thank you, Alessandro.
Yeah, thank you. Thank you for attending, and you've been super brave to do this on a Friday evening.
Would this be some form of post-processing?
Would this be some form of post-processing? So yes, absolutely. Could also be in processing, but I think it closely resembles post-processing. There's a very good correspondence between affirmative action and post-processing. Okay, I think we can call it a day. Oh, wait, there's a question. Are there any other high accepted standard rules of thumb for fairness like the 80-20 rule? Let's see. So 80-20 is recognized in the US, and it's not ideal. It is a rule of thumb, but it keeps. I mean, it's a little bit crazy. It's like if somebody drew a line on the sand, and then that sign sticked because it's a simple thing, and it's a little bit like not letting the optimal being the enemy of the good. So at least it's a starting point. It's like the first pancake that that comes out a little bit strange. And for all its limitations, that measure is still very influential. There isn't any other criterion that is as widely recognized as that measure, which doesn't mean that we should use the 80% rule all the time, but it means that it's still, as of today, a starting point.